In lesson 4, we're going to look at more with solving polynomial equations, and we're going to focus on two techniques. One technique being solving equations that are in quadratic form, and then another will be using a factoring technique that we learned in Unit 5, which is sum and difference of perfect cubes. So we'll be using that to help factor and then to solve. So the first section here is going to be solving equations in quadratic form, meaning these equations are in the form ax squared plus bx plus c equals 0. Now if you look at this first example though, you see that instead of just having an x squared, you have this x plus 3 quantity squared minus 2 times that same quantity minus 8 equals 0. So in this case, I have basically my x squared minus 2x minus 8 equals 0. So this is in quadratic form, even though it doesn't really look like it at first because you have this x plus 3 instead of just a single variable. So to make this a little bit shorter and easier to solve, instead of foiling everything out or using the box to multiply x plus 3 times x plus 3 and then distribute and then go from there to solve, what we can do, since this is in quadratic form, we can just let this piece that's not equal to a single variable, let it equal a variable. So for example, if I let y equal x plus 3, then what I can do is I can replace, so then I have, anytime I have an x plus 3, I'm going to put a y there. So I'd have y squared minus, so 2 times x plus 3, so I'm going to put a y, minus 8 equals 0. And then you can go ahead and you can just solve this. So this one looks like it might be factorable. So if we look at what numbers add to negative 2 and multiply to negative 8, or can we find numbers that add to negative 2 and multiply to negative 8? Well, the answer is we can, and we know that we're going to have opposite signs. So I'm going to go ahead and get my two sets of parentheses. I know that since I'm multiplying to a negative, I'm going to have opposite signs. And I'm adding to a negative, which means a bigger number is going to be negative. So it's going to be 4 and 2. And the 4 has to be the negative, so that when I add, I get negative 2. And then you can split this and you can set each piece equal to 0, since now you have a product being multiplied to equal 0. So I can go ahead, set each piece equal to 0, subtract 2 from both sides, so we get y equals negative 2. Add 4, we get y equals 4. So here are your two solutions. So remember though, this is the solution to this new equation that we created. So since we first let y equal some variable, now we have to take our two solutions and we have to substitute x plus 3 in for y. So I'm going to just write that out. So I'm going to substitute my original x plus 3 in for y. So I really have x plus 3 equals negative 2. And then I have x plus 3 equals 4. And now I can solve these and get what x is. So I can bring my 3 over. So we get x equals negative 5. Or bring this 3 over. We get x equals 1. So here are your two solutions to the actual problem, keeping in mind that we let x plus 3 equal y. So this is just another strategy. And again, I knew that this equation is in quadratic form because it was in the form of variable squared with some number, another, and then the variable minus a constant or plus a number. So it was the ax, there was no a, but I have x squared plus bx minus c. You also know that it's in quadratic form because this middle term is the square root of the first term. Notice here, this is always the square root of the leading coefficient. So that's how you know that it's in quadratic form. So let's look at some other examples. So this next example, again, I know that this is in quadratic form because if you look, this middle term is the square root of the leading term. So this is in quadratic form as long as I first bring it over, bring that 2 over, so it's set equal to 0. And then this is in quadratic form. So it's in quadratic form because the middle term is the square root of the leading term. So just like the previous problem. So even though it's an x to the fourth, the middle term is still the square root of the leading term. So what we can do is we can go ahead and we can just substitute a variable in for this middle term so that it looks as if it's in the ax squared plus bx plus c form. So what I'm going to do is I'm going to first let y equal x squared. And the reason, again, why I choose x squared is because I want my first term to be x squared, my middle term to be x, and then my c to be the number. So what I'm going to do is I'm going to substitute in. So I'm going to have 4y squared plus 7y minus 2 equals 0. And note that for this 4y squared, I got that because x, so let me just show you. If I have 4x to the fourth, this is the same thing as saying 4x squared raised to the second. So I let y equal x squared. So when I replace it, it's 4y squared equals 4y squared. So that's kind of how I did that. So then from here, what you can do is you can try factoring. You could complete the square. But again, completing the square, I wouldn't recommend just because you're going to have some messy numbers if you divide everything by 4. But you could do quadratic formula as well. So looking ahead, I know that this one is factorable. So if this were the first time I was doing it, I probably would do quadratic formula just because if you don't know if it's factorable or not. But I'm going to do this with factoring by grouping just because I want to review it with you. So factoring by grouping means you're going to multiply these two numbers, and you're looking for numbers then that multiply to -8 but add to 7. So what I'm going to do is I'm going to rewrite, so I have 4y squared. I'm going to rewrite this so that I have numbers that are multiplying to -8, but they need to add to +7. So the numbers that are going to work are going to be 8 and -1. So you rewrite this middle term as plus 8y minus 1y, and then you keep the minus 2 at the end. So then what we do is we split this down the middle. So I can factor out a GCF here. So I have 4y as a GCF. So I'm going to have y plus 2. And then here, we're trying to get a y plus 2. So we're going to have to factor out a minus 1. So I have a y plus 2 when I factor out -1. And then from there, you can go ahead and factor out y plus 2. So you factor out y plus 2, you're left with 4y minus 1 equals 0. And then from there, you can set each piece equal to 0 since it's a product equaling 0. And then you solve it. So subtract 2, we get y equals -2. So bring over the 1, divide everything by 4, we get y equals 1/4. And then your second step, so remember up here I let y equal x squared. So now what I'm going to do is I'm going to substitute my x squared back in for y. So I'm going to substitute x squared in for y. So since I let y equal x squared, now I'm going to take my equations that I just came up with, and instead of y, I'm going to put x squared in there. So x squared equals -2, and then you have x squared equals 1/4. And if you remembered, whenever you have a exponent in an equation, that's going to tell you how many solutions. So since this was to the 4th power, that means I'm looking for 4 solutions. So it's actually good at this stage that we are seeing x squared equal to a number, because now what happens is I'm going to take the square root, and whenever we take the square root of a variable, that's going to give you two solutions. It's going to give you the plus or minus case. And when you take the square root of a negative, remember we have our I, so I'm going to have plus or minus I square root of 2. And then here, I square root both pieces. Again, you have your plus or minus, and then when it's a fraction, you just square root the top, we get 1. Square root 4 on the bottom, we get 2. So here are your four solutions. You have plus or minus I radical 2 and plus or minus 1/2. So let's look at one more example in quadratic form just to get you familiar with it. And this one looks a little bit different, but it actually is in quadratic form. The reason why it's in quadratic form is because, again, that middle term is the square root of the first term. So this is in quadratic form because the middle term is the square root of the first term. So middle term is the square root of the first term. You can also look at this as it has, because if I have x plus square root of x minus 6 equals 0, this is actually the same thing as if I take that middle term and I square it, plus square root of x minus 6 equals 0. It's just they canceled it out because square rooting a number and squaring a number undo each other. But if you look, I have a number being squared, the square root, or just the number, and then the constant term. So again, it's in quadratic form because this middle term is really the square root of the leading term. But it's also because when you look at it, it's something squared plus something minus a number equals 0. So what that means is the middle term is always what you want to let your y equal or your other variable equal, just so that when we solve it, it's still considered quadratic form. So we're going to let y equal the square root of x, which then allows you to see, well, this is going to be y squared. This is going to be y minus 6 equals 0. So I'm going to go ahead and plug in. So I have y squared plus y minus 6 equals 0. And then this looks like it's going to be factorable. So I have two sets of parentheses. I'm going to have opposite signs. My bigger number is going to be positive. My smaller number will be negative to add to positive 1. Then you can split it, set each piece equal to 0. So we have y equals negative 3, y equals 2. So here are your two solutions. And then from here, remember, we have to substitute back in. So we're going to substitute x squared in for y. So we have the square root of x equals negative 3 and the square root of x equals 2. And now we're going back to those radical equations. Whenever you have a square root of a number and you want to solve, or square root of a variable and you want to solve it for that, you need to undo it. So it means you need to square both sides. So we get x equals 9. And then we square both sides over here. We get x equals 4. But because we're squaring, we're basically multiplying by an x, we need to check our solutions. So because of this type of equation, you can get extraneous solutions. So we need to remember to check. So if I take x equals 9 and I plug it into the original, so remember the original was x plus square root of x minus 6 equals 0. If I plug these in, so let's go ahead and plug in the first one. We're trying to see if this actually equals 0. So we get 9 plus 3 minus 6. I want to see if that equals 0. So 9 plus 3 gives me 12 minus 6. I get 12 minus 6 equals 6. Does not equal 0. So this solution actually doesn't check. So let's try the other one. So if I plug in 4 into my equation, let's see if that works. So we have 4 plus 2 minus 6, and I want to see if this equals 0. So we get 6 minus 6, which 6 minus 6 is 0. So my only solution here is going to be x equals 4. So just keep that in mind, that whenever you have square root functions, you have to remember to check your solutions, because you're adding in variables since you're multiplying by an x. When you're squaring something, you're really multiplying by that variable. So that's it for equations in quadratic form. The next thing and last thing in this lesson is going to be looking at solving equations using the sum and difference of perfect cubes. So when you look at this example here, you could bring over the 8, and then you could take the cube root of both sides to get x by itself, but you'd be missing solutions. So you have to remember, since it's an x to the third, that means that there's going to be 3 solutions. So what we're going to do is we have to look at factoring this. So this is going to be a difference of perfect cubes, because x to the third is a perfect cube and 8's a perfect cube. So I need to factor using difference of perfect cubes. So let's just recall. So the difference of perfect cubes, the formula for this is if you have a to the third minus b to the third, what that means is when you go to factor it, you take the cube root of each piece, so a minus b. You're going to square the first term. You change the sign. You multiply those. And then you add the last term squared. So you just square the b. So there's your formula for difference of perfect cubes. So now I'm going to apply that formula. So I'm going to go ahead, I'm going to cube root x to the third, which is just going to be x. Cube root 8 is going to be 2. And then I'm just looking at this x minus 2. I no longer worry about this part up here. So I just look at this x minus 2. So I square the first term, switch the sign, multiply the 2 and the x, so we get 2x, and then add the last term squared. So 2 squared is going to be 4. And then I keep the equals 0. So now, if you notice, we have a product being equal to 0. If we could, we would factor this further, but there's no numbers that are going to add to 2 and multiply to 4. So that tells me that when I split this down the middle, I'm going to have to do quadratic formula or completing the square to this right-hand side. So I'm going to go ahead, I'm going to set each piece equal to 0. And we're going to solve them. And remember, we're expecting 3 solutions. So one of my solutions is already done, x equals 2. But for this other side, I have a little more work to do to figure out the solutions to this equation. So up to you, you can do quadratic formula or completing the square. To me, it seems like completing the square might be the better choice here, or the easier choice, because I have a leading coefficient of 1. So I'm going to do that just again to refresh your memory as well. And to complete the square, you bring over the 4, so it's going to be x squared plus 2x equals negative 4. And then remember, we draw out our square, and we split these pieces. So we split up x squared, so it's going to be x and x. This is the x squared. And then we need to split up this 2x, because together these have to be 2x. And we have to split it up evenly, so it's going to be 1x and 1x. Which means up top here, you split the number to positive 2 in half, which is going to be plus 1 plus 1. And then you're going to multiply to get the number that goes here. 1 times 1 is going to give me positive 1. So that means I'm going to be adding positive 1 to both sides. So I have x squared plus 2x plus 1, which we already have. Basically, if you multiply x plus 1 and x plus 1, you're going to get x squared plus 2x plus 1. So the factors of x squared plus 2x plus 1 are just going to be x plus 1 squared, because it's repeated. And this, when you combine your like terms, is going to be equal to negative 3. We're going to square root both sides, so we get x plus 1 equals plus or minus, I have a negative radical 3, so that means it's going to be I times radical 3. And then I'm going to bring that 1 over. So it's going to be negative 1 plus or minus I radical 3. And there are your other two solutions because you have a plus and you have a minus case. So you have three solutions. So one last problem that'll be using the sum formula. So this problem here, if you notice, you have perfect cubes. So this is going to be the sum of perfect cubes. So if you recall the formula from Unit 5, whenever you have a to the third plus b to the third, so perfect cube plus perfect cube, this is the same thing as taking the cube root of each piece, leaving the format, squaring the first term, switching the sign, multiplying these two terms, and then adding the last term squared. So there's the formula. Let's go ahead and apply that. So I have 8x to the third plus 27 equals 0. First thing I'm going to do is take the cube root of each piece and keep the plus sign. So cube root of 8 is 2. Cube root of x to the third is x. Cube root of 27 is 3. And now I ignore the original equation and I just look at this new piece. So I square the first term. So squaring 2x. So square 2, you get 4. Square x, you get x squared. You switch the sign, multiply the 2. So 2x times 3 is going to be 6x. And then you square the last term. So 3 squared gives me 9 equals 0. So then what you're going to do is you're going to go ahead and you're going to set each piece equal to 0. So we have 2x plus 3 equals 0. And we have 4x squared minus 6x plus 9 equals 0. And then what you're going to do is solve these both for x. So again, because this was something raised to the third power, there should be three solutions. There's one solution over here, so 2x equals negative 3. Divide both sides by 2, we get negative 3 over 2. So there's one solution, and I should be getting two other solutions from this quadratic. And in order to solve this quadratic, I wouldn't guarantee that it's factorable. You could try factoring it, but if you looked at it for completing the square, it's not going to work out very nice because you have a leading coefficient of 4 and you can't divide by 4 easily. So this is one where I would use the quadratic formula. So I get negative b plus or minus b squared minus 4ac all over 2a. So I'm going to go ahead, I'm going to plug in, I have negative, so a, b, c. So negative 6 is in for b, plus or minus negative 6 for b, squared minus 4a, which is 4, c is 9, all over 2a. So then you're going to go ahead and you're going to simplify, so we get 6 plus or minus 36. So minus 4 times 9. So minus 144 over 8. So we simplify underneath the square root. We get negative 108. And then you're trying to break down this radical 108. So let's break that down off to the side. So we have negative 108. Bring out the I, perfect square, non-perfect square. So the biggest perfect square that goes into 108 is going to be 36. And it'll be 36 times 3. So we'll get 6i radical 3 left. So let's go ahead and plug that in. So this is going to go back into our equation. So it'll be x equals 6 plus or minus 6i radical 3 all over 8. And then again, remember, you can reduce as long as you can reduce in this pattern. So we have 6 over 8. So 6 over 8 is going to be a fraction, but you can divide basically the top and bottom by 2. So if I divide the top by 2, I'm going to have 3. If I divide the bottom by 2, I'm going to have 4. plus or minus, and I'm going to have the same exact thing. 6 over 8 is going to be 3 over 4 I times radical 3. So you have your second set of solutions. So you have x equals negative 3 halves plus this set here. And again, I didn't know if this was factorable by looking at it, but instead of going through the whole factoring by grouping process and then figuring out it doesn't actually work, you could just use a quadratic formula. And it wouldn't have been factorable because you have an imaginary solution in there. So that's it for this section. So these are just more examples of solving quadratics or solving polynomials in different kinds of formats.